So now I want to talk about the concepts of a linear transformation and a matrix transformation. And so I've got a definition here, and then I've got a problem to work on. It's more based in theory than computation, which is the way a lot of these problems in linear algebra are. But so I wanted to talk through it. First, the definition of a linear transformation. So a transformation is basically a function. You input a vector, you get one vector for your input, you get one vector for your output. It's just like definition of a function. One input gives you one output. It's got this special name here when we talk specifically about when the input is a vector and the output is a vector. So in this case, T is a transformation from Rn to Rm. It's linear if for all input vectors u and v, so all vectors u, v, and Rn in this case, T of u plus v is equal to T of u plus T of v. So it doesn't matter if you add the vectors first and apply the transformation to the sum, or if you apply the transformation to the vector u and then apply it separately to v and then take the sum of those two outputs, that you get the same result either way. Doesn't matter if you add the vectors first or if you apply the transformation first and then add. Or if you kind of think of it as we're distributing the transformation across a sum. That's a special trait. We call it the operation preserves addition when you can kind of distribute it in that way. Which, by the way, just to give you an idea of when is this not true, with trig functions, if you have sine of a sum a plus b, it's not just, if you remember your trigonometry, that's not just sine of a plus sine of b. There's a whole, we call them the angle addition formulas for that. I mean, in this case, it's like sine of a cosine b plus, how did I just say it? Sine b cosine a. I don't want to get in the weeds with that, but just the point is, there's an example of a function that doesn't have this property. Other property of linear transformation, so it's got to satisfy both of these, is that you can pull a scalar out front, basically. If you have a scalar times a vector, you get the same result if you apply the transformation to that product, or if you just do the transformation of the vector u and then multiply by c after the fact, but the result is the same. So these are the two properties that are required in order for a transformation to be considered linear. Now, this example is going to lead us to a theorem. We're being asked to show that if T is a transformation from Rn to Rm, it's got to be a linear transformation whenever there's an n by n matrix A such that T of x is just equal to that matrix A times x. So if we can write a rule that looks like this, where the transformation of x is just a matrix times x, we call that a matrix transformation, by the way. This would make T a matrix transformation. This is an F. And we want to show that when T can be described with a rule like this, then it's got to be a linear transformation. That's the goal here. So if we want to show that it's got to be a linear transformation, then we got to show that it satisfies each of these properties here. And it has to satisfy these, notice, for all vectors u and v in the domain. So you don't get to just pick, here, let me do T of 1, 0 and 0, 1 or something like that. You can't pick any specific vectors. We got to show this works for all vectors in Rn. Now, the way this is going to work is using properties of the matrix vector product that you guys studied in, I think, section 1.4. So we're going to use some properties of this matrix vector product to show that it's linear. And if you remember those properties, then it's fairly straightforward to show this. All right, so anyway, enough jabbering about it. So in this transformation, let's just go for this first property. T of u plus v. Let's assume that u and v are vectors in Rn. Then, okay, I want to follow, I'm trying to color code this. I want to follow this rule right here. So we're assuming that T of x is equal to A times x for some n by n matrix A. So this is equal to A times the input, u plus v. And here's where the properties of the matrix vector product come in handy. So if you look back at your properties from section 1.4, A times a sum, u plus v, for these are vectors in Rn, is equal to A times u plus A times v. This right here is a property of the matrix vector product. Oops. Okay. And A times U, well, that's, according to this definition, AU is equal to T of U. This is equal to T of U. And AV is equal to T of V. So there we go. T of U plus V is equal to T of U plus T of V. So we've shown that it satisfies this first property. Now I want to go for the second one. So here we're showing property number 1. Now we'll go for property number 2. T of some scalar C times U. So again, according to this definition, that's equal to A times CU. And so again, go back and look at your properties in 1.4. There's a property that says if you have a matrix times a scalar times a vector, like this, we can pull the scalar out front. So this is equal to C times AU. And AU, according to this definition here, this is equal to T of U. So this is equal to C times T of U, which is what we wanted to show. Now we've shown that T of C times U is equal to C times T of U. So it satisfies this property. So therefore, T is a linear transformation. So the upshot here is this gives us a way, maybe an easier way in a lot of cases, to show that T is a linear transformation. If you can come up with a matrix A, and you can show that A times X is going to give you T of X for every input vector X, then it's got to be a linear transformation. We're saying that every matrix transformation is a linear transformation, according to the proof here. Okay, so I warp speed forward here so we can employ the basically the theorem that we just proved with example 2. So we just showed that any matrix transformation, which is any transformation that can be expressed as T of X equals A times X for some matrix A, any matrix transformation is a linear transformation. So we want to use that now to show that a transformation defined here is a linear transformation. The idea is I'm going to express this transformation as a matrix vector product, A times X. So then we can say, well, this transformation happens to be a matrix transformation. Therefore, by the work we just did, it is a linear transformation. Now, and let me just say, if you tried to go at this thing directly, so if you tried to go directly for the properties, okay, let me show that, so if I've got this one vector u, I'll call u1, u2, plus another vector v, let me call it v1, v2, and then try to do a lot of work using the formula, and then eventually prove that this is equal to t of u1, u2 plus t of v1, v2. It's going to be a lot of work. It definitely can be done, but it's going to require a lot of writing, a lot of pretty tedious work. So this idea of expressing it as a matrix transformation saves us a lot of time and effort. So my goal is to express this right here as a matrix A times the vector x, x1, x2. That's my hope. And let me talk for a second about the dimensions of this matrix A. So notice that the input is a vector in R2, and the output is a vector in R3. So this is a transformation from R2 to R3. And maybe in the end we'll note the dimensions of the matrix A that we come up with. All right, so if I want to break this down into a matrix vector product, one thing I would notice is, okay, I've got a bunch of multiples of x1 and then a bunch of multiples of x2. So let me take this right here and break it down into, let me first separate these vectors. So I've got all these multiples of x1. I'm going to make that its own vector here. And then I've got all these multiples of x2. So negative x2, negative 4x2, and 5x2. Okay, so first I'm just separating out the components here, the x1 components and the x2 components. And then notice, okay, well here I've got this common multiple of x1, so I'm going to pull that out. So this is x1 times, I'm going to write the coefficients of x1. Remember that if you don't see a coefficient, then we assume the coefficient is 1 there. And then same thing here. I've got I see across these terms, I've got this common multiple of x2. Let me factor that out. And then write the coefficients here. So negative 1, negative 4, and 5. And then when you take a step back and look at this, well, that looks like a matrix vector product right there, where these guys are the columns of A. 2, 3, 1, negative 1, negative 4, 5. And these are columns. I don't want it to look like subtraction there. Times the vector x1, x2. So this x1, x2, this is our input vector x. And this guy right here is our matrix A. We actually call, there's a name for this matrix right here. We call it the standard matrix for the transformation. So now that we've expressed it as a matrix vector product, then, again, it's because of those properties of matrix arithmetic. Well, okay, so now I can say if I have A times U plus V, that's the same as A times U plus A times V. That's a property of our matrix arithmetic. And A times CU, this is what I did in the last example, but just to reiterate, is equal to C times A of U. So it can be, it preserves addition, it preserves scalar multiplication, it's a linear transformation. Now we can just say, as soon as you write it as a matrix vector product like this, if T of x is equal to A times x, then T is linear. Linear transformation. And then I knew there was one more thing I wanted to say. So just note the dimensions of the matrix A. The number of columns of their standard matrix should match the number of entries in your input vector, x. So because this is a transformation from R2 to R3, A is going to have 2 columns, and the number of rows should match the size of your output vector. So if this output vector has 3 rows, then that should be the number of rows in your matrix A. So in this case, 3 rows. So when T is a transformation from R2 to R3, if we express T of x as A times x, if we write the standard matrix for a transformation like this, then that matrix A is going to be, well, in this case, let's see, we do rows by columns, so 3 by 2. So when T is a transformation, if T is a transformation from Rn to Rm, I just want to generalize this real quick, then when you express it as a matrix transformation, A is going to be an M by N matrix. It's going to have M rows, because it's going to match the size of your output, and N columns. The number of columns should match the size of your input vector.